So I want to talk about a very theoretical direction of work, which is characterizing PAC learnability beyond binary classification. So, same thing. So we all know the fundamental theorem of statistical learning is that if we want to do binary classification prediction, then we have a clean characterization in terms of the base dimension. So that's kind of the basic, called the fundamental theorem of statistical learning. And the question that we want to ask is, can similar characterization be provided to other learning tasks? So for example, can we do a clear characterization of multi-class prediction when you have more than two classes? Or can we do a clean characterization of unsupervised learning of probability distribution? Do we have characterization so nice as the visit dimension when we go to other learning tasks beyond binary label prediction? So we have what I want to talk about here is our family of recent results in the direction. Everybody who knows me knows that if I have results, they are negative. Results from a few years ago with this group of co-authors is that if there is a problem which is called the generalized statistical learning model, and in that model we showed that there can be no dimension that characterizes learnability. So that was kind of a first result of proving that for some meaningful learning problem there exists no characterization. We cannot hope to find any dimension. And very recently with my student Tosca, we got a bunch of further results of a somewhat similar flavor, and we showed that for a variety of learning tasks, including unsupervised learning of the probability distributions, learning with respect to a family of data generating distributions, the PAC model tells you you should be able to learn with respect to any distribution, but if you restrict the family of distributions, can you characterize when things will be learned? Or learnability with respect of real-valued functions. For all of those problems, we showed that there can be no dimension that characterizes learnability. So what I want to talk about here is just describe those results and give you just a very high-level idea. So the first question we have to ask, if I want to show you that there is no dimension that characterizes learnability, I need to define what do I mean by a dimension that characterizes learnability. Otherwise, I won't be able to show you that it doesn't exist. So we consider two types of what do we mean to characterize learning. One type is we call quantitative. You want that this dimension will tell you what is the learning rate. That's what the visit dimension does. It not only tells you if it's learnable or not, it also tells you how many examples you're going to need. The other type is more relaxed, just be qualitative, just give you notion of dimension that will tell you, is this class learnable or not learnable, without talking about rates. So these are two types of notions of dimensions, and we have to define each of them. So for the quantitative, what we want is that you have some class, you have a class of models, and you want to have a dimension that takes a model and gives it a number, assigns to it a number, and then you want to have a function, which is a sample complexity, that when you get epsilon and delta, all you need to know about the class is just its dimension, and you will know how many examples you need. That's what happens with the visit dimension. If I give you the visit dimension of the class, now you get epsilon and delta, you know how many samples you will need in order to hit this goal, and all you needed to know about the class is its visit dimension. So in other words, we want a dimension such that all the information about the class that you are shooting, that you need for estimating samples, is just the dimension of the class, no other information about the class. That's the notion of a quantitative dimension. And then there is a qualitative dimension, just trying to tell you whether a class is learnable or not. And here again, we say, okay, what could be something that kind of in the spirit of the BC dimension, we have a countable set of properties, and we say that, so for every W is a countable set of properties, and we say that if a task, if a class satisfies each of those properties, then this class is not learnable, but if it doesn't satisfy some of them, it is learnable. Think again of the VC dimension. Say the properties are my VC dimension is greater than D. So if my VC dimension is greater than D, for every D, I'm not learnable. And the other thing that we kind of take is we want it to be finitary in the sense that if you satisfy one of those properties, then you have a finite evidence, a finite subset of your class, such that everybody that will contain this finite evidence will also satisfy the property. So think of the BC dimension, say the property is Q shuttles a set of size D. So if Q shuttles set of size D for every D, it will not be learnable. And we also have the property that if Q shuttles a set of size D, I can pick a finite subset of Q, such that any class with this finite subset will shuttle a set of size D. So we have a finite subclass which evidence to this hardness. So that's our notion of a qualitative dimension. That's what. So we have very general requirements of what do we mean by a dimension that characterizes learnability. And now, with respect to those, how does the common known dimensions meet these requirements? You can see that all of really everything that's been discussed in the literature is the characterization of some type of learning. VC dimension, Littlestone dimension that talks about online learning, fetch chattering dimension, each of the dimensions that we can find in the literature, not only those that have been shown to characterize learnability, but also everything has been conjectured to show something that we don't know. All of them meet our requirements of what a dimension should be. So now that we have such requirements that everything that we know of meets the requirements, it is meaningful to have theorems tell you for that problem, no dimension can satisfy those requirements. And that's the results that we get. So we got the first result was in 2019 with this group of co-authors. We showed that no dimension that will satisfy these requirements could characterize learnability with respect to the generalized statistical learning model. I will not tell you what the model is. What I want to mention here is that proof technique here was very kind of special proof techniques. We used tools that come from set theory. We created, using forcing, two models of mathematics such that the class will have the same dimension, no matter what dimension it is. It'll have the same dimension in both models, but in one model, the class will be learnable, and in the other, the class will not be learnable. So it shows you cannot come up with a dimension that characterizes learnability, because the dimension will stay unchanged between the two models, but learnability will hold in one of them and fail in the other. So we used a heavy tool from axiomatic set theory, forcing, in order to show that no dimension exists for this type of problem. And that was with a big group of very strong authors. And recently we got the results with Tosca. And those results are not published yet, but we showed, we used other tools to show the lack of dimension, non-existence of dimension for the other problems. So for the qualitative dimension, we used a notion from infinite combinatorics of cofinality. If you have an ordering, the cofinality of an ordering is the size of the largest sequence that will get all the way, will be unbounded in your order. So if you take the real numbers, if you want to get to the end of the real numbers, you want to dominate every real number, you can settle for a countable set. The natural numbers are a countable set, it's cofinal in the real numbers. So this notion of cofinality is what we used. We showed that if we look at the rates of sample that you need in order to learn probability distributions, the cofinality is not countable. And therefore, any dimension that takes values as natural numbers or real numbers cannot quantitatively characterize learning distributions. So we use this trick of cofinality, and for the showing that you cannot find any qualitative characterization, this is it's a more relaxed notion of dimensions, so we needed to work harder to show that they don't exist. And here we had some kind of a trick. We said, if you have your family of properties that claim to characterize learnability, then we pick some class that is not learnable. If it's not learnable, then it satisfies all the properties. Think of it, if it's not learnable, then for every D, it shatters a set of size D. But then we were able to create another class that has all those evidences, but is still learnable. So we showed that we cannot meet those true properties. That if we cannot at the same time say, if you satisfy each of those requirements, you are not learnable, but each requirement is manifested by a finite subset. We can take all of those finite subsets, put them together, and still be learnable, so there can be no such dimension. So we show that there can also be no qualitative dimension for all of this long list of problems. So yeah, I just wanted to give you a teaser, and I'll be happy to discuss it further if anybody is interested. Thank you.